Welcome to this video, about part of AC500 Controller Basic Training course. In this video we will show you how you can backup variables values, like operating hours or parameters. After completing this video you will be able to distinguish the behavior of retentive and non-retentive variables. Create all types of retentive variables. Decide what kind of retentive variables is the best for your application. And finally, reset the retentive variables. We distinguished between two types of retentive variables of AC500: the persistent variables and the retained ones. Persistent variables maintain their value by project download. They are appended to the program code. Retained variables maintain their value after power supply off. For CPUs of type PM57X, PM58X and PM59X, this functionality is given only with battery. For types PM55X and PM56X, the battery is not needed. The retentive variables are stored in the flash EEPROM. The variables can be declared as persistent, or retain, or both. Additionally, in the AC500, you can declare an addressed memory area as both persistent and retain. To explain the declaration and behavior of the retentive variables, we will use a small project. This project contains 3 independent up counters. We will test the different behavior of the counters depending on the declared variable types. They will count the same pulses and can be resetted by the same variable. For the second and third of them, the counted value should be buffered by program download and by lost up power supply. In this case, due to keep the value, the counter instance is to be buffered. The CPU must be equipped with battery and the project is nearly ready, except the setup for buffered %R area, and variable declaration for the function block instances. Let us start with the declaration of buffered %R area. In the Control Builder Plus, double-click on the branch CPU parameters. You see in the right window the list with the CPU parameters. For this example, let us define 5 words to be buffered. They should be located in the beginning of the area. In the row Start Persistent %RBOX, the first address remains 0, which means the start address of the buffered area is %RB 0.0. In the next line, End Persistent %RBOX, we fill 9 because 10 bytes fill the same area as 5 words. We update the configuration file by right-click on the branch AC500, and selecting the item, Create Configuration Data. We acknowledge with OK the warning that by the next program transmission the CPU will be stopped. We needed this manual update because the project editor is already open. The editor will be automatically displayed. In the first counter, the current value should not be buffered. We will create the common variable for the CTU instance. Let us name it CTU not retentive. It is to be a local variable to be shown in this video on the same screen and from type CTU. The behavior for the global variable is the same. We confirm the declaration with OK. In the second counter, the status should be buffered. We will create a retain and persistent variable for this instance. Let us call it CTU retentive and be a local variable from type CTU. Now we activate the options retain and persistent by setting the checks in the appropriate fields, and confirm the declaration with OK. In the third counter, the status should also be buffered. We will create the buffered persistent variable from the address %R area. Let us name it CTU retentive R area and be a local variable from type CTU. Now we activate the options retain and persistent by declaration of the address from buffered %R area. Let us take the first address, %RW 0.0, and confirm the declaration with OK. Please never use both configuration options for buffering for the same variable. Now, we will send the project to the controller, and test the behavior of the counters. After the program was sent to the controller RAM, we send the boot project into the flash EEPROM. Next, start the controller by clicking on Menu Online and Item Run. Now, we are going to generate some input pulses. What happens with the counted value if we stop and start the controller again? What do you think? Let's try it. The value is kept for all outputs. What happens if we reset the controller and start it again? Let's try. We recognize that the reset is initializing the not buffered values. 5 new pulses are generated. Now, all counter have again values unequal 0. Now, what happens after reset cold and restart? We recognize that the reset cold is initializing all variables, but the %r area keep their values. The reset original would erase the project, the whole configuration and all variables. For this it is not relevant for the test and we won't try it. 5 new pulses are generated. All counter have again values unequal 0. Let us switch off the power supply of the CPU. The communication error is occurring because the controller is off, and the connection got lost. We switch the power supply again, and we log in the controller. We recognize that power supply off is initializing the not buffered values. All retained values remain. Thank you for attending this video. If you want to learn more about a scalable AC500 controller, please use the following link. Or if you have an additional technical questions, you can contact our helpline support. For general comments and questions about this video, don't hesitate to contact us.